All right, let's start. So, yeah, we are currently discussing about RNN, or recurrent neural network, and yeah, um, I hope you played with the simple toy code called minchar RNN that basically performs this given any arbitrary paragraph that you give to run this code. Yeah, so yeah, in my case, I used some paragraph that describes my short biography to that code, and then it generated a reasonably good sentences and paragraphs and so on. And that I believe that code that minchar RNN is based on this original RNN code, not the LSTM or GRUs, but at least for this character level sequence generation with the not much of a with the small size the training data, it should work fine. Okay, and conceptually this is one example figure in our slide that performs this character level language model. Did I explain what the language model is? Okay, language model is for example, suppose we heard about these two words while we discuss. While we do the conversation with our friend, and then suppose we didn't hear about this word, and then based on these two words that we previously heard, we can predict what word should appear in this place, right? It could be something related to study, right? So it will not be like computer games or maybe some desk or chairs or or any other kind of non-academic or nothing related to this study materials, right? So we can at least think of some predictable or reasonable words that we can expect in that place, right? So that is a kind of language modeling task that we perform in our own brain. Okay, so let's imagine a set of our vocabulary words. So in English, there exists maybe 1,000 different words. Okay, and then given this 1,000 different words, we can actually consider the probability of each word appearing in this place. Okay, and then it will be represented as a 1,000-dimensional probability vector, right? So if some words that appears likely in this place will have a higher probability, right? Such as a math or science or maybe deep learning, and those words is quite reasonable to appear in this place to go along with this word study, right? So those words will get a high probability, but some other words that are not related to this kind of studying, and these words will have a lower probability. Okay, so computing these probabilities, is called language modeling. Okay, so this is basically a language modeling task. So given these two, this is a language modeling in the character level. So given these two characters, we can think of the probability of each character appearing in the next place, right? So for example, L can appear with a high chance, but maybe some other words, some other characters like A or K or something like that. I mean, suppose there exist no words starting with H, E, and A or K. Suppose there exists no such words that starts with these three characters, and then we can think of the probability of appearing, of this observing this character K will have a zero probability, right? So that is also the language modeling task at a character level. So this RNN model basically performs this language model, okay? Okay, so here it is one example of a many-to-many model, right? So yeah, we are given an input sequence, and then at each time step, we have to produce each output at each time step, right? Okay, and so okay, let's move on. So here, what is the basic RNN cell in this model? So for example, this green rectangles are our main RNN cell. So what was the RNN's input and output setting? So let's remind ourselves that this RNN setting is represented as this ht minus 1, and xt will be given as an input, and ht at the current time step t will be our output. Okay, that is just the main or basic building block of RNN, right? And then using this RNN as our basic module, whether we design our task as a many-to-many or many-to-one or one-to-many, yeah, it's up to ourselves to stack more layers in an input level or at an output level. So in this case, this is time step 1, 2, 3, and 4, right? And then given the second time step, and then it took the input as this xt or x2, and this is a ht minus 1 or h1 at the current time step of t equals t being equal to 2, and then this is producing ht or h2 at this time step, right? So up to this point, so this is just a RNN's basic setup. Okay, so there will be just the same in all the almost all the models, like many-to-one or many-to-many or one-to-many and so on. Okay, and then if we want to have a many-to-many model, and then using these h1 and h2 and h3 and so on to produce, we use it to produce the output in the whatever form that we want. So if we want to have each character as an output at each time step, and then using this hidden state vector, we stack another layer. Here in this case, we stack the linear layer in this case, and then that linear layer is represented as this form, W, H, Y, and H, T. Okay, so in this case, this W, H, Y is the linear transformation matrix that was stacked given this as an input, and then it produces this output, right? And this is an output that was produced, and then we generate, we stack another layer of a softmax, okay, to produce the probability over all the possible vocabulary words that we have. So in this case, we have a 4 letters or 4 unique characters in our vocabulary, right? So we produce this 4-dimensional softmax or probability vector. Okay, and yeah, if we want to perform many to one, for example, and then yeah, we don't actually need to produce these outputs in the middle, right? And then in that case, we only stack this linear layer at the final time step of 4 to produce this output. And then if for example this keywords, I mean these words are having a positive or negative sentiment words, and then we can supervise it as a binary classifier, right? So we can just reduce it to a one-dimensional output or scalar output, and followed by the sigmoid nonlinear layer, and then supervise it as a 0 or 1, depending on whether this word is a positive or negative sentiment word. Okay. And what about the what about one-to-many case? One-to-many case. So in one-to-many case, there are two different settings. So the first setting is that, yeah, just like the case, we didn't produce these outputs because we want our task as a many-to-one, right? So now we want a one-to-many setting, and so yeah, we just removed this part. And so in the case of one-to-many setting, similarly, we can just remove this part, right? So in this case, how can we remove them? We can just simply provide or supply 0 vectors at the next or subsequent time steps, right? So we just simply provide the 0 vectors, okay? Or, yeah, or in this case, yeah, in this character level RNN or this language modeling task, I mean, if you ran the code of this minchar RNN, the only input that we need to trigger this language modeling or this character level sequence generation task is to provide just one single character in the beginning. Okay, it could be just a single, a particular character, or it could be start of sentence or start of word kind of special token. Okay, but anyways, let's just assume that we just supplied or provided a single character in the very first time step. Okay, and in this case, we generated the predicted output of the next time steps character as E, for example, and then as shown in this figure, we can provide this output as a predicted output, whether it is correct or not. Okay, because it's just a prediction of our model, right? So we don't know yet whether it is correct or incorrect output, but anyways, we can provide it as the input to the next time step for our RNN module. Okay, so this is the two possible approaches to perform one-to-many RNN kind of setting. Any questions? Okay, and then so this is this is a test time kind of the scenarios that we use this model for the test time, but in the case of training time, I mean, back to this let's just forget about this one-to-many or many-to-many stuffs, but let's just discuss about this character level language modeling task itself. So in this case, in the case of training time, there are two different strategies of training, depending on whether we provide. The main difference of two different training strategy is based on the input that we provide during our training. So let's see. Okay, so in this case, so this is the slide about the training time, right? And then here we know that the ground truth at the first time step is E, because the E is the next character after this L, H, not L, but H, right? But here, what is our prediction? Yeah, when looking at this logit value, so this is our vocabulary, H, E, L, and O, right? So here, our output from this probability is the character O, right? Instead of the true answer, E, right? So in this case, yeah, we will apply our ground truth, and then using the softmax loss, we will generate the gradient with respect to each of these logits, right? So what will be our gradient with respect to these 4 logit vector? So if you studied the derivation of the gradient of this softmax layer, and then the gradient arriving at this logit vector will be this guy, right? So 1 and 1.2 and -3 and 4.1 will be our gradient vector, right? Because our ground truth vector will be 0, 1 and 0, 0, which is a one-up vector indicating the character E, right? Okay, so we will just train based on this gradient, this layer and this layer and so on. But here in the current time step, or in the current iteration of this gradient, anyways, we produced this character O instead of the ground truth character E, right? So in this case, if we just utilize this this strategy that we use to trigger this one-to-many kind of setting by supplying this character that we produced in the previous time step as an input to the next time step. So in this case, here, even though the ground truth is E, but we currently produced O as the most likely output, right? And then this O should be provided in the next time steps input, right? So here, we didn't, during our training time, we didn't provide this predicted output from the previous time step, but instead we provided the ground truth output from the previous time step, right? So you can you see the difference between these two? So here, whether we produce the correct output or not, in the next time step to trigger the next time step's RNN, we can provide the ground truth input, okay, or we can provide this potentially wrong or incorrect output that was generated in the previous time step. Okay, so depending on these two different strategies or scenarios, both of these both of strategies are possible when training this RNN module, and when using this ground truth values. Okay, so when using the ground truth value, even if you didn't provide, or even if you didn't generate the ground truth output as a prediction in the previous time step, okay, so if we provide these ground truth outputs from the previous time steps, okay, and then it is called teacher forcing. Okay, and if you provided this potentially incorrect output produced by the previous time step in your model, so that is the case not using this teacher forcing. Okay. So between these two scenarios, which one do you think is faster in terms of the training? Which one do you think is the faster strategy for training? Yeah, depending on whether we provide a ground truth input or potentially incorrect outputs from the previous time steps. Okay, so here, this is a teacher forcing case that provides this ground truth, ground truth sequence as an input. I mean that, the training for that teacher forcing case is faster than the other case. Okay, so if you think of this scenarios, and then let's say this produced this O as a kind of potentially incorrect output. Okay, so in this case, the next character will be O without using a teacher forcing, right? So in this case, the the currently generated sequence will be H and O, right? So in this case, if your model at the current time step of time step T is really behaving correctly, and in that case, it will be really difficult to generate this correct output of an L, because H, O, and L doesn't make sense, right, in this case, right? Although, there could be some words that start with this H, O, and L, and so on, but if there is a correct word of this hello, H-E-L, and then, in order to properly produce the correct output of L at the time step 2, and then at least it should provide the correct output, so that we can expect this RNN cell can properly behave to produce the correct output. Okay. Any questions about this teacher forcing? 네, 하여튼 한글로 다시 한번 설명을 해주면, 이 아웃풋에서 이제 각각 캐릭터들을 하나씩 맞는 거를 생성을 해야 되고, 이제 여기서 이제 첫 번째는 E를 생성해야 되고, 두 번째는 L을 생성을 해야 되고, 이게 우리가 생성해야 되는 캐릭터들이죠, 각각의 타임 스텝에서. 그리고 이제 요 그라운드 트루스 레이블을 우리가 각 타임 스텝에 걸어갖고 이제 학습을 진행을 해요. 건다는 거는 이제 그 그라운드 트루스 원합 벡터를 이제 소프트맥스 로스를 통해서 저 로직 값에다가 이제 걸어준다는 거죠. 근데 이제 중요한 게, 여기서 트레이닝 과정 중에는 당연히 이제 제대로 된 캐릭터를 이제 생성을 안 했을 수 있고, 그러면 어떤 타임 스텝에서 이제 제대로 된 캐릭터인 E가 아니라 이제 다른 거를 생성을 했다. 그러면 그 다른 거를 이 다음 타임 스텝에 이제 입력으로 넣어주는 게, 이게 이제 티처 포싱이 아닌 거예요. 티처 포싱이 아닌 거고, 이때는 이제 잘못된 캐릭터가 들어왔으면 벌써 여기 네트워크가 이제 제대로 이렇게 동작한다 해도, 여기서 이제 우리가 이제 그러니까 우리가 이제 기대할 수 있는 맞는 캐릭터인 L이라고 하는 거를 생성을 하기가 좀 더 어려운 거죠. 그래서 이제 처음에 학습이 안 됐을 때는 이 각각의 이제 previous time step들에서 이제 무슨 캐릭터들이 막 생길지 모르는, 혹은 이제 맞는 캐릭터가 아닌 막 이상한 캐릭터들이 많이 생기는데, 이제 그것들을 다 그 다음 타임 스텝에다가 이제 우리가 전파를 해주면, 그러면 이제 그 다음 타임 스텝에서 잘 하려고 해도 이제 뭔가 이제 잘못된 인풋이 그 전에 이제 잘못된 게 생성이 됐으니까 이미 뭔가 상황이 좀 뭔가 망가진 그런 상황에서는 뭔가 제대로 된 캐릭터를 생성하기가 좀 어렵다. 약간 이거가 되는 거예요. 네, 그래서 이제 티처 포싱을 하는 게 좀 더, 네, 그러니까 여기서 이제 제대로 된 것을 생성을 했든 안 했든 그 다음 타임 스텝에서는 이제 제대로 된 캐릭터를 넣어줌으로써 이제 그 전 단계에서 이제 잘못한 거를 우리가 좀, 네, 바로 잡아서 제대로 된 거를 항상 그 입력으로 그 다음 타임 스텝에 넣어주는 게 이제 그 각각의 이 모듈들을 학습을 하는 게 좀 더 용이하다 이거고요. Okay, and then between these two scenarios, there are also several differences between them. So another difference that that we can discuss as the difference between them is in terms of a parallelization, or batch processing, this teacher forcing can be performed much faster. Okay, so what I mean is, so this is a main limitation of the RNN, which is not being able to be parallelized. Okay, so here in this case, suppose we didn't produce the output yet, so the computation is still being done. Okay, so GPU is currently computing the forward propagation and then computed this hidden state vector at the time step of 1, and then produce this logit and then this output word as an O, right? And then this O is provided in the next time steps input in the case of non-teacher forcing. Okay, in the case of not using the teacher forcing, and then we have to wait. In order to perform the forward propagation in the next time step, we have to wait for the output to be computed in the previous time step, right? So that way, this next time steps for the propagation should wait until this previous time steps output is generated. Okay, but in the case of teacher forcing, we don't need to wait for this previous time step's output was generated, because we already have the ground truth sequence. Okay, ground truth sequence, and so we can just immediately provide each time steps input characters, right? So that way, it can be more easily parallelized in the case of teacher forcing. Okay. But still, in this case, teacher forcing, even if we use the teacher forcing, this RNN cannot be fully parallelized, and it is because, so for example, in this cell, what kind of input do we need? The input from the current time step, xt, and then we also need the ht-1, right? So ht-1 is this guy, which has to be computed based on the previous time steps input and the previous time steps hidden state vector, right? So this so from this recursive formula, like this, okay? So here, we have to produce this ht-1 in order to compute this ht. So among the computation of these ht across different time steps, they cannot be parallelized. Okay, so in this case, we have to wait until this guy to be computed in order to update this value, and then in order to compute this guy, we have to update or obtain the second time steps hidden state vector. Okay, so this is the main limitation of this RNN. which is not being parallelized due to this recursive relationship between ht-1 and ht. Okay, and so you guys understand this backpropagation through time, and also this truncated backpropagation through time, which is sometimes called BP-TT. Okay, and I believe min-char RNN is also using this truncated backpropagation through time. So in the case of min-char RNN, suppose this is our input paragraph, okay, and then we need to set the max length or the sequence length in order to form our batch or this truncated batch across the different time steps. So here, suppose our sequence length is 10, for example. In this case, 1, 2, 3, so this whole sequence of these characters are well over the 10 number of characters, right? So it's probably maybe 100 or so, right? But in this case, we don't use these entire character sequences as a single training sequence, but we can, we actually truncate or basically cut them into pieces for each 10 character sequences. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be, so this will be our first mini batch. Okay, so the first mini batch will have the input as, so here, start of maybe sentence, special token. So this is our special token that we use in order to indicate, we are about to generate our character sequences starting from the next time sequence. Okay, so from here, including this SOS token, and then up to this point. Okay, so just like from HELLO, and then we provide HELL, and what is our output in this many-to-many setting? It will be ELLO, right? So we actually do the same thing on each of these truncated pieces of these character sequences, so with the length of 10. Okay, so so this is one mini batch that we compute this forward propagation and also the back propagation. Okay, and then starting from the next batch, we just treat these sequences as if the whole sequence started from this character E, right? So we just ignore the previous part, okay, and then we start from scratch or all the way from the beginning. We start with this character E in the next mini batch. Okay, so that is the meaning of this truncated backpropagation through time. But I mean, that is a meaning of the truncation, but backpropagation through time is so our loss is applied at each different every time step, right? So if we produced maybe O instead of E in the case of a hello example, and then this one will apply the ground truth label of E, right? And then the loss will be generated from the logit at this time point, and then also it has its own ground truth value at the next time step, and so on, right? And so the loss or the gradient was generated from here, and then it actually reverses or goes back in a reversed order from this forward propagation, right? And so from here, WHY is trained or updated through our gradient descent or back propagation, and then this guy, WXH, okay, which is corresponding to this forward propagation path, will be generated as our gradient with respect to this parameter in this xwh. Okay, and then the loss will also be incurred over here, and then it will also be generating the ground gradient with respect to why once again, and then it is actually going back through time, right? So that way it's called the gradient descent or back propagation through time, because it's actually going in the reverse direction of our time. Okay. Let's see. So here the gradient coming from this direction with respect to this why, and then another gradient coming from this direction with respect to why. So we have two sets of the gradient, okay, assigned to why, right? And then what happens, these two sets of the gradient assigned to why. So we have two sets of the gradient assigned to the why, and then they will be added together, right? And then conceptually, if we redraw this computational graph of this RNN, and then it is like we have why, which is our matrix, or the linear transformation matrix, and then it is multiplied with over here and over here and so on. So it is branching out into these two different paths, and then the gradient coming from these two branches will be added together to update this why. Okay. And then here, let's see. Okay, so when if you guys remember this figure, and then at every time step, the core operation of the RNN is to take the ht-1 and xt, and then it produces ht. Okay, and then we described or discussed it as a linear transformation, or one affine or linear or fully connected layer that transforms these inputs into this output. But the nonlinear unit that we use is 10H, right? So in this case, let me just redraw this, where ht is a two-dimensional vector and xt is a three-dimensional vector, and this is an ht, and okay, so this is our xt and ht-1, right? So this is nothing but just a linear transformation of w and this concatenated input of xt and ht-1. Okay, and then I want to point out one simple characteristic here, which is that, so if ht is a two-dimensional vector, and then what is the dimension of w? W is 2 by 5, right? And xt is a 3-dimensional and ht is a 2-dimensional vector, and this 2 by 3 part in our entire W matrix, let's call it as WXH, and the next part as WHH. Okay, so in this case W is this concatenation of this 2 by 3 and 2 by 2 matrix. Okay. Okay, so WXH will have a 3 columns, and WHH part will have 2 columns, right? And then we know that these 4 different numbers will work as a linear combination coefficient of these columns, right? And this guy will be multiplied with the first column, and this guy will be multiplied with the second column, and so on, right? And then it will be just the sum of these 5 different weighted columns, right? The columns are weighted or multiplied with each coefficient, and then they are added together, right? And then how about representing this in this form? WXH times XT plus WHH times HT minus 1. So in this case, so this part is this guy, okay? And our XT is over here, and WHH, which is our square matrix, and we have our HT minus 1, right? So this representation and the lower representation is exactly the same, right? Because these 5 different columns are just grouped into 2 matrices, right? So they are separated into 2 matrices, and then still these linear combination coefficient of these 3 are placed over here, and over here they will be placed over here, right? Okay, so these 2 representations will be exactly the same, right? Okay, and then here, we forgot one thing, which is, for example, 10H, considering the nonlinear unit, okay, that will eventually produce our HT, okay. So our RNN is designed as a one fully connected layer concatenated with the 10H as a nonlinear unit. Okay. So let's discuss about the basic nature of this original RNN. So let's imagine a simpler case where HT and XT is just one-dimensional scalar values. Okay, scalar values. So in this case, so the RNN cell at this time step will be computed as follows. Because they are just a single number, okay, so let's just imagine that they are just one-dimensional scalar value, and then in this case HT can be represented as 10H as 8 times xt plus b times h t minus 1 plus c. Okay. So considering our bias terms, and then these two will be working as the linear combination coefficient, where this a will be w xh and this guy will be w hh. Okay. Okay, so in this case, let's imagine some gradient arriving at this point. Okay, at this point. Okay, and then if we redraw this RNN cells, and then it will be having a tan H, right? This tan H will have its own gradient, okay, which is definitely less than 1. So it is actually ranging between 0 to 1/2, right? So this will be the some gradient corresponding to this tan H, right? And then yeah, this HT, okay, so let's call it as YT, and yeah, we consider DYT corresponding to this node, and then DYT will be multiplied with some value corresponding to the slope at this tan H value, and then okay, HT to this YT. Now, yeah, suppose that is also represented as this form, D times HT plus E, which is our YT. Okay, so this one will be corresponding to WHY and HT, okay, and some bias vector. Okay, but anyways, yeah, DYT times this gradient value corresponding to this tan H layer will produce this DHT, right, which is the gradient corresponding to this the node HT, right? Okay, and then yeah, I want to discuss about the gradient about this B. Okay, so we have HT minus 1 here. Okay, so let's call it as XT minus 2 and HT minus 2 just by setting this layer's time step as T. Okay, and then this DHT, yeah, we apply this tan H, and then we arrived at this node, right, just before the tan H, and then this output is corresponding to this part. Okay, and then what about the gradient with respect to this HT minus 1 and this B? Okay, so here, in the case of gradient of HT minus 1, from the gradient at this point, okay, this point, yeah, is represented as this linear combination, and then the gradient with respect to HT minus 1 will be B, right, because the linear combination coefficient with respect to this HT minus 1 is B in this case, right? So the gradient will be multiplied by B when moving from the gradient over here to the gradient over here, right? So sorry for a little bit messy figure, but yeah. So just to simply saying, let's think of the gradient arriving at this linear combination node, okay, and then considering the gradient with respect to this ht minus 1, okay, and then we will just multiply the gradient at this node by this b, right? Okay, so that is the gradient with respect to ht minus 1, right? ht minus 1, and then ht minus 1 generated at the previous time step. We'll have also the recursive formula just like that, which is ht minus 1 is 10h and axt minus 1 plus b times ht minus 2 plus c, right? So this will be the same formula or common formula that we apply by using the recurrent neural net, right? Okay, and then the gradient arriving at this ht minus 1 will also be multiplied by the gradient or the slope, produced by this 10h, which is also ranging between 0 to 1/2, and also when considering the gradient assigned to this assigned to this ht minus 2, okay, we will also multiply this b once again, right? Okay, so moving from ht to ht minus 1, we have to go back or back propagate 10h layer, and then also we have to back propagate this linear combination layer, which will produce the gradient as b, okay, and then the gradient arriving at this ht minus 1, and then let's consider ht minus the gradient arriving at this ht minus 2, okay. So in this case, the gradient will also backpropagate through the another 10h layer, and also we will just multiply b once again, okay. So my point here is that the gradient, backpropagation through time or through time step is very much like multiplying this b or this linear combination weight assigned to this previous time steps hidden state vector. We keep multiplying that value over and over, okay. Okay, so basically that is a main limitation or main problem of this recurrent neural net, in its original form, not the LSTMs or GRUs. So in the case of a gradient or the backpropagation through time, the gradient will be multiplied with this b over and over, okay. So if b was more than 1, okay, b is greater than 1, and then we keep multiplying the same value which is greater than 1 over and over, which will be easily exploding, okay. Or if b is small, okay, so the absolute value of b is smaller than 1, and then the gradient will be will become smaller and smaller with the this exponential growth or the shrinkage, okay. Or it can also be viewed from the backpropagation as well. So suppose you stored some meaningful information at this time step, okay. So ht minus 2 was maybe 2, and this was really useful or very critical information to generate some outputs in the far time steps ahead, okay. So in this case, if this value should have been 2.1 or 1.9, for example, so just this correction or adjusting these values into the optimal value will be done by our gradient descent or this backpropagation, right? But the correct gradient was coming from this time step, which is far apart from this time step. Okay, so suppose the gap between these two time steps are really far apart. So in this case, the gradient coming from here will be either like multiplied over and over, right, by the factor of b, right? So if b is greater than 1, and then the gradient coming from this point will easily explode into really large number, or if it is smaller than 1, and then the gradient will become easily just close to 0, right? So that is the main limitation of this gradient exploding or gradient vanishing, which is notorious for training this original form of the RNN. 한글로 다시 설명해 줄게요. 결국 이게 이 영어 단어를 찾아봤는데 지오메트릭 시퀀스? 지오메트릭 시퀀스가 뭔지 알아요? 지오메트릭 시퀀스가 등비수열이라는 뜻이 있더라고요. 등비수열. 기하 뭐 하여튼 기하 평균. 이 두 개 곱해서 루트 취하는 게 기하 평균이잖아요. 하여튼 이게 등비수열 같은 역할을 좀 해요. 그래서 여기서 뭔가 생성된 어떤 정보가 저 멀리에서 뭔가 영향을 끼쳐야 된다라고 하면, 그러면 그 정보가 이제 forward propagation 측면에서 보면 여기서 ht-2가 이 심플한 시나리오에서 보면 b랑 곱해지죠. b만큼 커진 거예요. b가 뭐 1보다 작으면 b만큼 작아졌다라고 볼 수가 있어요. 하여튼 b배만큼 커졌다라고 생각하면 그 값은 다른 값과 섞여서 이 10h를 통해서 ht-1으로 이렇게 뭔가 변신을 하죠. 그래서 여기서 있었던 정보가 일단 그런 forward propagation을 거치게 되고, 그러면 어찌됐건 그 값은 그 next time step의 ht-1은 다시금 또 b를 또 곱해서 그만큼 배율로 커지고, 또 거기서 물론 10h에서 이렇게 레인지가 잡히긴 하지만 어찌됐건 결국은 타임 스텝을 건너갈 때마다 여기서 있었던 정보는 계속 b를 곱하게 되는 거예요. 그러니까 이게 등비수열이라는 이야기를 이제 내가 하게 되는 거죠. 그러면 이제 forward propagation 측면에서는 이제 b를 계속 곱하는 그런 측면이 있고, backward도 똑같아요. backward도 backpropagation도 결국 그 b랑 곱해졌으면 b를 b가 곱해져서 이제 backpropagation도 넘어오잖아요. 그러니까 우리가 뭐 이런 거 이제 y는 w, x 이런 것처럼 이게 그러니까 그냥 뭐 y는 3x다. 그러면 이거는 뭐 우리가 열심히 유도를 했듯이 이제 dx는 그러니까 이제 거꾸로 건너올 땐 w 트랜스포즈에 dy로 이렇게 건너오죠. 이런 식으로 건너와요. 근데 이게 상수면 결국은 dx는 뭐냐? 포워드 할 때 이게 곱해진 만큼 이 곱해져서, 왜냐면 3이나 3 트랜스포즈가 똑같으니까 여기 이렇게 되는 거예요. 그럼 이게 결국은 y와 x가 이게 이제 ht-1이고 이게 ht다. 그럼 얘네들은 하여튼 이렇게 타임 스텝 하나 건너서 이게 그러면 이게 dht-1이고 3의 트랜스포즈 혹은 3 곱하기 dht니까 이제 타임 스텝을 이제 건너서 백프랍을 할 때는 이제 3이라는 값이 계속 곱해진다는 뜻이에요. 그래서 이제 뭐 등비수열이라는 이야기를 쓴 거고요. 물론 이제 탄 h가 중간중간에 한 번씩 있으니까 탄 h가 이제 0에서 이제 2분의 1 사이니까 이게 값이 무한정 커지는 거를 방지해 줄 수도 있지만, 그렇지만 뭐 탄 h가 무슨 값일지는 우리가 잘 모르는 거고, 그리고 그 탄 h의 어떤 값으로 우리가 인풋으로 들어가게 될지는 이제 얘네들에 의해서도 또 결정이 되고 하니까 하여튼 그 값이 뭐 그 값을 우리가 컨트롤할 수는 없는 거고, 어찌됐건 그레디언트가 결국은 그 탄 h에서 나타나는 그 값들의 곱과 더불어서 이제 그 아까 여기서 b라고 부른 그 값을 이렇게 타임 스텝 거슬러 오게 되면 이제 n번 이렇게 된다는 뜻이에요. 그래서 하여튼 그레디언트가 이렇게 이제 익스플로딩을 하기 때문에, 그러면 이 HT 이렇게 멀리, 이렇게 과거 멀리 있었던 요 HT의 뭐 얘가 뭐 아주 뭔지 모르겠지만 얘에 대해서 그레디언트가 뭐 폭발적으로 커졌다, 폭발적으로 작아졌다, 뭐 그게 어쩌라는 거냐, 뭐 그게 이제 그거 자체가 또 중요하다기보다는 이제 결국은 얘가 그 전에 있었던 HT-3을 만들어낼 때 이거 백프랍은 또 우리가 할 수 있죠. 근데 중요한 건 HT3에서 HT2를 만들어내고 HT2에서 HT1을 만들어낼 때 걸리는 요 파라미터 B 있죠. B에 대해서는 그레디언트가 뭐냐? B에 대해서는 그레디언트가 뭐냐면 결국은 여기서 여기 땅까지 넘어온 그 그레디언트에다가 결국은 요 HT-1이라는 거를 곱한 게 B에 대한 그레디언트죠. 이게 곱하기 게이트는 그레디언트의 이 뭐죠? 스위처라고 했으니까. 그렇죠? 그러니까 어찌됐건 그레디언트 HT에 대한 그레디언트들이 막 폭발적으로 커져 있으면 그러면 결국은 걔랑 어떤 같이 이제 곱해지는 저 B에 대한 그레디언트가 결국은 폭발적으로 커지게 된다는 뜻이에요. 아니면 아예 없거나. 그래서 그 B를 그러면 제대로 업데이트를 아예 안 하거나 아니면 B를 엄청 큰 값으로 이제 하게 되기 때문에 그래서 이제 gradient vanishing 프로블럼이 발생을 한다. 뭐 이거거든요. 네. 이 포인트는 이해가죠? 이해가요? 한글로 설명해도 안 되면 할 수 있는 방법이 없는데. 네. Okay, so this is called the notorious problem of long-term dependency. Okay, so I'm not sure if I pointed you to this website called Unreasonable Effectiveness of Recurrent Neural Network, and this post is about, not just about the RNN, original RNN, but it's actually it's just considering the LSTM and GRUs as well. So this shows various different and also quite interesting character level RNN example or language model examples. So this one shows that our lecture slides was originally created by this guy called Andrei Karpathy. Okay, so this one is some Shakespeare example, and it produces, as you saw in the lecture video, it produces this LaTeX code. Okay, so you will write your proposal using this LaTeX code, right, in the overleaf, and also it is the example of language modeling. Character level sequence generation by using some code snippet written in the C++ language. Okay, so in this case, so this is really the character level language model generation example. Okay, so here there is a various interesting characteristics here. So the first one is it is properly doing the indentation of when generating this code. Okay, so suppose you opened a curly bracket once, and then after this curly bracket, even though it doesn't show this particular character, so for example, this after curly bracket, although it is not shown, it is it generated the carriage return or this line change character. Okay, so that's why it produces the characters, the subsequent characters in the next line. Okay, so we change the line over here. Okay, and then it does a proper indentation. So because we opened this bracket, it actually adds two space or two of these blank characters of this and this, and then after generating these two blank characters, and then it now starts with generating this I and T, and, yeah, I and N and T and so on. Okay. Okay, so here in this example, let's look at this if statement. So after generating these sequences in this if statement line, and it also generated another curly bracket over here, right? And then it generated the carriage return, and then in the next line over here, okay. So in this case, it produced 4 different space or the blank characters of the first and second and the third and fourth, and then finally after generating the four consecutive space characters, and then it produced this backslash or maybe slash. Okay. So when looking at this RNN character level generation example, we can see that this RNN module actually can do the countings, okay? Because if it produced like 3, okay, up to, so far in the previous time step, suppose, we produced 3 space characters in a row, and then it knows that it has to produce another character, one more time, okay, and then at the next time step, it knows that it generated 4 space bars, and then now it's time to generate another character of this, maybe slash, like this, okay. So it means that our RNN module can properly do this counting operation. Okay? So this is one kind of interesting stuff, right? So here, this is time step 1, and this is time step 5. So some hidden state information that was produced in the first time step needs to properly convey the information or give the some meaningful information to this time step of 5. Okay, so in this case, there are some time gaps between these 4 different characters between time step 1 and time step 5. Right? So it can be viewed as one example of this long-term dependency. Okay, so in the case of an RNN, original RNN, this kind of counting operation or this meaningful or interesting behaviors may not, they cannot be properly generated, okay, because if there was a wrong information generated in this time step, and then this information needs to be given in the 4 time steps ahead, and then the backprop, if it generated the wrong characters, so it produced another space or maybe some different characters, and then it will be supervised by its own ground truth character, and then the backpropagation or this proper error or the gradient information should be properly transmitted into this 4th time step before, right? So in this case, if some information, some gradient information generated at this time step, that information should be given properly into the long time step before. Okay. So that information shouldn't be, basically, that shouldn't be exploding, or that shouldn't be vanishing. Okay. In that case, this proper kind of counting operation cannot be properly learned. Any questions about it? Okay, and then so there are several other interesting examples in this blog, and so one thing that we can kind of analyze when training this character level RNN model is, so our hidden state vector of H1 and H2 and H3 and so on. So these are not scalar values, right? So scalar values are just a simple example, but in general it is a multi-dimensional vector, right? So it could be 64-dimensional vector or 128-dimensional vector and so on, right? And then we can actually analyze the behavior of this hidden state vector in terms of what kind of information does it actually contains. Okay, so in this case, one experiment that we can do is we actually pick up one particular dimension of our hidden state vector. Okay, so here this is a first time steps hidden state vector, and this is the second time steps hidden state vector, and then we fix the dimension. We fix the dimension that we observe as, for example, 1. Okay, and then we just observe or collect all these values at each different time step. Okay, and then we just color code them. Okay, so if this value is small, and then we just color it as blue, and then if it is large, and then we colorize it as a red color. Okay, and then we can do the same thing on this the first dimensional value, and then maybe second dimensional value, and so on. Okay, and then if we have maybe a 64-dimensional vector of our hidden state vector, and then we can extract out, or we can visualize 64 different dimensional kind of color patterns across different time steps, and these are the examples. Okay, so here we can see many interesting examples. So let's see. Okay, so in this example, so here I think the green one is the encoding. The green color is encoding the largest value. Okay, so in this case, let's look at what characters have the green colors for a particular dimension of this hidden state vector. So here, green one is shown or found in www and this URL, and also it was found in another character sequences that also is the URL form, right? And also another URL form has a similar color pattern, right? So it means that a particular dimension is actually we can view this recurrent neural nets each hidden state value or dimension as a kind of our memory cell. Okay, so each dimension is playing a role of memorizing some particular information, and so here that memory cell or that dimension is playing a role of like indicating whether these sequence or these character sequences in the current time steps are URLs or not. Okay, so if they start to generate the URL sequence or the character sequence, and then that particular dimension is actually turned on or having a high activation value. Okay, and this is another interesting example. So here the blue color is a small value, and the red color is a large value, and then this is this long sequence of characters, right? And then at the end of each line, it starts to become red, and then in this case, it can be viewed as like storing the number of characters. Storing the information of the number of characters that this sequence produced without using the carriage return, or since the last carriage return, how many characters it produced. I mean, such kind of information is stored in that particular memory cell or hidden state dimension. Okay, so here, after this in the fact, okay, so how did this model change this line to start with another line to generate this sequence of these characters? Okay, that is because it actually produced a line change or this carriage return characters at the end of this line. Okay, so again, I am a boy, and then this is tedious, but and so on. But here, if we change it the line, and then even though it is not shown, it means that we generated this special characters at the end of this previous or first line. Okay, and then in order to generate this particular line change characters, okay, it actually a particular cell is memorizing or storing how many characters we generated, okay, without since the last carriage return characters. Okay, so it was once just staying as almost zero value, and then after some characters were generated without generating any line change characters, and then it starts to read. Okay, so it's becoming larger and larger, and then at some point, as an output, it generates the carriage return characters. Okay, and then another one is this quotation mark indicator. Okay, so this is another interesting cell that we can observe the behavior of, and this this is an if statement, if statement detector. Okay, and also another thing is comment detectors that starts with this slash star. Okay. Any questions about this example? 네.
히든 유닛을 각 셀마다 디텍하는 게 가능해요?
네. 각 디멘전마다 서로 다른 밸류들을 저장을 하니까, 그러니까 각각마다 역할이 있다라고 보면 돼요.
그 중에서 하나를 뽑아서?
네, 하나만 딱 프로브를 하는 거예요. 하나만. 한 놈만 이제 딱 보는 거예요. Okay, so in these examples, we discussed about this long-term dependency, right? And these examples were not actually the result from the original RNN. So these results are from the example of this LSTMs, okay, not the original RNN, okay, because the original RNN cannot carry this long-term dependency, or cannot carry the useful information across a long time range. Okay, so in this case, let's see. So in this case, it has to remember that, okay, now it opened this parenthesis as a left parenthesis, and then it stays a high value, and then after a really long sequence of maybe 30 to 40 characters later, and then it just produces the right parenthesis that closes this if statement, and then it now starts to become small value, right? Okay, so this is pretty long-term dependency. Okay, so these models or these character level language generation or language modeling task or example were produced by LSTM model, not just the original RNN model. Okay, so to summarize, the point is that this RNN suffers from this long-term dependency. So that's why we mainly use this LSTMs or GRUs. Okay? And the main reason for suffering this long-term dependency of the original RNN is because RNN is just like a geometric sequence that just keeps multiplying the same values over and over in the forward pass and also in the backward pass. Okay, so we have some image captioning. Okay. Yeah, although not much time is left, but yeah, I'd like to briefly discuss about this LSTMs, yeah, which is really important. So when using the RNN in these, any of these recent work that deals with this text or any other types of sequence data, the original RNN is not used at all. Yeah, almost it is not used at all, and instead this LSTMs or GRUs or gated recurrent units are mostly used in the place of this RNN cells. Okay, so in this long short-term memory or LSTM is like, so originally in the case of an RNN, it really suffers from this short-term memory, but it actually extended this short-term memory into a long version. Okay, so that's why we call it as a long short-term memory. Okay, it's like extended short-term memory or improved this short-term memory compared to the original RNN. And okay, so here this LSTM is almost having the same same structure in terms of an input and output. So what is the basic input and output setting of this RNN? So this is the basic formula, right? And this RNN module, which is typically composed of one single fully connected layer followed by the 10H. Yeah, it is now extended into much more complicated structure. Okay, and also this LSTMs, and this LSTM has actually two different versions of this hidden state vector, which is called the cell state. Okay, this is a cell state and HT-1 or this hidden state. Hidden state vector. Okay, so you can view this hidden state vector as now two different sets of vector called cell state or this hidden state vector. Okay, but still the main input and output is still the same. Okay, so this is a recurrent formula, right? And now, where is this cell state? So it is actually kept inside of this LSTMs, right? So it's like kind of internal memory that this LSTM maintains. Okay. Okay, and so in the case, in this LSTMs, again I mentioned that we have these two inputs, xt and ht-1. Okay, and then here we have xt and ht-1, right? And here, just for the sake of simplicity, I mean, just to simplify the situation, we actually think of the dimension of this xt and ht or ht-1 to be the same as each other. Okay, so here the dimension of xt is also h, and ht-1 has the dimension of an h. Okay, so it now takes the input vector whose dimension is 2h, and we have a linear transformation matrix similar to original RNNs. Okay, and then in the previous case of our LSTMs, RNNs, we just directly produce this HT, right? But in this case, we don't directly generate this HT, but we generate four different four different vectors that has the same dimension as ht. Okay, so if we had these two h dimensions as our input, and then in the case of original RNN, and then our w would be just like h by 2h, but we don't just generate one ht vector directly, but instead we just generate four different set of vectors through this linear transformation, and thus we have the size of 4h times 2h. Okay, and then given these four different vector sets, and then we apply different nonlinear units for each of these four different vector sets. So for three of them we apply sigmoid, and for the last one we apply 10h, and then it has its own name: input gate and forget gate and output gate, and it is called like gate. Okay, and then so this is our overview of this LSTM cell. Okay, and then here we have two different sets of the hidden state vector. So one being just ht or ht minus 1, and also another set which is called the cell state, which is internally kept in our LSTM module. Okay, but you can just treat it. You can just think of it as just another version of ht or ht minus 1. Okay, and then now which one is playing a major role between the two? This cell state is more important. Okay, so this ht will just follow, or this one will be just an output of this cell state. Okay, so the cell state itself is really the important part. Okay. Okay. Okay, so cell state will follow this formula. So suppose cell state is just a two-dimensional vector of maybe 3 and -2. Okay, and then we have our previous time step cell state vector. For example, it is like, let's call it as let's set it as 2 and -1 instead of this ct. And then this one is our hidden state vector, and then this forget gate is the sigmoid output from this second vector. Okay, so that is the output from the sigmoid. So each of the output is ranging from 0 to 1. So suppose it's 0.1 and 0.8, and then it's like 3 times 0.1, which means we only maintain the 10% of the original information from the first dimension, and in the case of second dimension we maintain 80% of the information, which results in 0.3 and -0.4, 2.4. Okay, so that way it's like so this is really called the forget gate, which means that we want to remove some portion of the information across different dimensions from this previous cell state. Okay, and then we have an input and the gate and their element-wise multiplication, and then this is the updating formula of our cell state. Okay, and so so the time's up. So let me point out one really important part, and I'll try to continue as quickly as possible in the next lecture to finish this LSTM and GRU. But here, the main equation form is like, so this is basically the recursive formula between CT-1 and CT, right? So between these two, there is no common recursive formula, because our F and I and G. So they will become different. So this is a FT and the IT and GT, which is the output that was generated by this linear transformation, and then followed by this each of these different nonlinear units. Okay, so at every time step, our FT and the IT and GT will become different vectors, and thus it's no longer applying the same formula over and over onto this cell state, right? So we no longer are restricted by the common formula or this kind of geometric sequence by keeping multiplying the same value over and over. So we are no longer restricted by that. So so that way we can maintain long-term dependency much better compared to the original RNNs. Okay, so I will just quickly continue how it works in the next lecture. Okay, thank you very much. And also in this week's Wednesday lecture, so I'll be out of town. So one of my students will actually explain or go through our exam problems. Okay.
아까 말씀한 티처 코칭 그거랑
네.
CS 이전에 강의도 말한 샘플링으로 산다는 거랑은 다르죠.
네, 샘플링으로 하는 거는 이걸로 하면 일단은 소프트맥스 벡터가 이렇게 나왔잖아요.
네.
그러면 여기서 이제 우리가 두 가지의 방식을 쓸 수가 있어요. 아웃풋을 만들어내기 위해서. 그러니까 첫 번째 방식은 뭐냐면, 지금 여기서 이제 만약에 우리가 클래시피케이션 아웃풋을 한다 그러면 여기서 프로바빌리티가 제일 많이 나온 얘에 대한 어떤 클래스 아웃풋을, 그러니까 최종 아웃풋을 내겠죠. 그러니까 이거는 디터미니스틱한 방법이고요. 그러니까 argmax라는 어떤 룰을 적용을 해갖고 이 확률이 다른 애들보다 높은 애, 걔가 무조건 아웃풋으로 이제 나오는 방식이고요. 근데 이제 그렇지 않고 이 확률 분포에서 우리가 랜덤하게 여기서 샘플링을 할 수 있어요.
네.
그걸 얘기를 한 거거든요.
네네.
그러면 이제 여기서 이제 같은 그러니까 아웃풋을 이걸로 뽑았다라고 하면은 이제 이 다음에 나타나는 시퀀스는 여기서 나타나는 이 2를 다음 타임 스텝에 넣고 이렇게 이제 테스트 타임에서 이렇게 쭉 아웃풋을 뽑아낼 때는 같은 모델이면 같은 캐릭터를 시작하면 언제나 이제 똑같은 아웃풋만 나와요.
네.
그렇죠? 네. 근데 이제 여기서 서로 다른 걸 좀 뽑을 수가 있다라고 한다면 물론 확률은 좀 적지만, 그러니까 H2에서 2가 나올 확률은 13%밖에 안 되지만 어쨌건 얘도 뽑힐 수는 있잖아요. 그럼 이때는 이제 캐릭터 시퀀스가 이제 다른 시퀀스가 나올 수도 있는 거죠. 같은 모델에 같은 입력을 하죠. 약간 그거를 이야기를 한 거고, 이제 이게 이제 어떤 문제가 있냐면 여기서 지난번에도 비슷한 학생이 이야기했는데 스터디 매스 베리 하드라는 문장을 생성을 해야 된다. 이게 워드 레벨의 뭔가 그 랭귀지 모델링이다라고 하면 I 다음에는 이제 우리가 동사를 이제 생성을 해내야 돼요. 근데 어떻게 해서 I가 들어왔을 때 그 다음에 나오게 되는 단어를 스터디가 아니라 여기서 뭐 예를 들면은 뭐 very라는 단어를 여기서 이제 very hard 이런 얘기가 있는데 이제 이 very라는 단어를 어떻게 해서 얘가 잘못해서 먼저 이렇게 생성했어요. 이게 확률이 다른 애들보다 약간 더 높아갖고 어떻게 해서 이게 생성이 됐어요. 그럼 이 경우는 이미 문법적으로 이제 틀린 잘못된 문장이잖아요. 그래서 여기서는 더 이상 이제 뭔가 회생 불가능 아니면 복원이 이제 안 되는 거죠.
어떻게 보면 그냥 이 13%라는 이 확률을 그냥 100%를 눌러주는 방법이에요. 그냥 어떻게 보면
그게
이게 너무 낮을 수도 있다는 거 아닌가요?
그러니까 이제 여기서 디터미니스틱하게 한다는 거는 여기서 2를
네.
항상 2를 뽑는다는
네네.
거고요. 여기서 이제 랜덤 샘플링을 한다는 거는
네.
여기서 비록 13%의 확률이긴 하지만
네네.
그래서 굉장히 적은 확률이긴 하지만
네.
2가 뽑힐 수도 있다라는 뜻이에요.
네네.
그러면 이제 아웃풋도 이제 이런저런 아웃풋이 이제 다른
네.
아웃풋들이
아.
나올 수가 있잖아요.
네네.
그래서 이제 서로 다른 아웃풋들이 나올 수가 있고
네.
뭐 하여튼 그걸 얘기를 한 거고 이제 그거를 하면 이제 이게 어떻게 되니 그게 좀 뭐 빔 서치라고 하는 게 또 있거든요.
네.
그러니까 빔 서치라는 게 있는데 이게 뭐냐면 이제 HLLO라고 이렇게 생성이 됐으면
네.
얘가 생성될 확률은 0.84죠.
네.
그리고 얘가 생성될 확률이 여기서 또 2가 들어가고 2가 들어갔을 때 그때 이제 소프트맥스 프로바빌리티에서 제일 높은 애를 뽑는다. 디터미니스틱하게 뽑는다. 그러면 얘가 예를 들면 0.26이에요.
네.
그러니까 뭐 얘가 0.25, 0.25, 0.24 해갖고
네.
얘가 0.26이면 어쨌건 얘가 뽑히겠죠.
네네.
그럼 얘도 또 0.26밖에 안 돼요.
네.
0.26밖에 안 돼요. 그러면 우리가 이때 이제 조인트 라이클리후드를 계산할 수가 있어요.
네.
그러면 이 우리 모델이 생각할 때 이 전체 이 HELLO를 생성하는 그 아웃풋에 이거를 이 시퀀스를 생성할 확률은 뭐냐면
네.
0.84 곱하기 0.26 곱하기
예.
0.26 곱하기 0.26이죠.
네.
그렇죠?
예.
그런데 이제 여기서 예를 들면 이 0.13을 내가 생성을 했어요.
네.
그러니까 우연찮게
예.
얘를 랜덤하게 샘플링을 했단 말이죠.
예.
그러면 여기서의 확률 값은 완전히 이제 다른 값이 나올 수가 있겠죠.
아 예.
그러면 그때 뭐 제일 큰 애가 확률이 예를 들면 0.95였고
네.
그 다음에도 나오는 게 뭐 0.88이고 그 다음에도 나오는 게 0.92다 이렇게 나왔으면
네.
결국은 얘랑
어.
우리 모델이 생각할 때는
오른쪽 없이.
얘가 더 좋은
아.
아웃풋이라고 생각을 하는 거예요.
아 네네네.
그렇죠? 랭귀지
네.
모델 측면에서
네.
보면
네.
전체 시퀀스를 놓고 보면 이 아래쪽 게 더 생성이 될 확률이 더 높다라고 생각을 하는 거죠.
네네.
근데 이제 이거는 지금 우리가 첫 번째로 하는 이 그리디 어프로치, 그러니까 첫 번째 타임 스텝에서 하여튼 argmax로 개를 뽑는 게
네네.
전체 시퀀스 측면에서는 우리 모델의 기준으로 봤을 때조차 그게 어떤 가장 옵티멀한 결과를 뽑지 못하게 될 수도 있는 거죠.
네네.
그래서 이제 그런 랜덤하게 이제
그게
샘플링
이게
하게
샘플링
되면
얘기였고.
네.
아. 그래서 아까 캡을 하던 게 이 샘플링하고 방금 아까 티셔 폴싱하고 대등한에서 하나 고르는 건지 지금 같은 얘기를 하고 있는 건지 아니면은 아예 다른 얘기하는데 제가 지금 둘이 같은 거라고 뭔가 같은 대등한 부분이 헷갈린 건지.
그건 다른 거예요.
아.
그러니까 티처 폴싱이냐 아니냐는
네.
여기서
네네.
이제 랜덤하게 뽑았든 아니면 디터미니스틱하게 argmax를 뽑았든
예.
argmax를 뽑으면 2가 나오고
네.
랜덤하게 뽑았으면은 뭐 13% 확률로
그 2가 나올 수도 있겠고.
그렇죠. 이거 5가 나오고.
예.
그렇죠.
예.
근데 얘네도 그러니까 어쨌건 내가 랜덤하게 뽑았든 디터미니스틱하게 뽑았든 누군가를 뽑아서 그 다음에 그 내가 뽑은 거를 그 다음 타임 스텝에 인풋으로 넣어주는 게
네네.
이게 티저 보싱이 아닌 거고요.
아 예.
티저 보싱은 여기서 내가 랜덤하게 뽑았든 아니었든 그거를 뭘 뽑았든지 간에 그 다음 타임 스텝에는 내가 항상 맞는 그 그라운드 트루스를 넣어주겠다는 거죠.
네네.
근데 이게 티처 폴싱은 기본적으로 트레이닝 할 때 가능한 거예요.
네네네.
트레이닝 할 때만 가능하지 테스트 할 때는 그냥 여기서 생성한 거를 이 다음에 넣어주는 방법밖에 없어요.
네네네.
네.
아 네. 그럼 아까 샘플링 할 때 처음에
네.
애초에 2를 넣었을 때 뭔가 모델을 잘 판단하게 하려면
네.
어느 정도 학습이 된 상태여야 그렇게 판단할 거 아니에요. 처음에 그러니까 이전의
네.
상태가 아니라.
이거요.
네네.
이 확률이 그러니까 뭐 이게 더 좋은 거냐?
네.
그러려면 이 확률 자체가 믿을 만한 확률이어야
학습이 얻은 이후에.
그렇죠.
예.
네.
아 네. 일단.
그래서 이걸 하여튼 그 디코딩 네. 그러니까 이제 그러니까 학습을 할 때는 그러니까 티처 폴싱을 최소한 내가 티처 폴싱을 쓴다 그러면 내가 그 전 단계에서 내가 잘못 뭔가를 생성을 했어도
네.
잘못 생성을 했어도 그거를 그 다음번에 영향을 받지 않아요.
네네.
그렇죠?
네.
근데 이 테스트 단에서는 지금 어쨌건 그 전 단계에서 뭔가 생성한 게 있으면 그거를 무조건 그 다음 타임 스텝에 입력으로 넣어줘야 되는 거거든요.
네네.
그러니까 이 경우는 이게 뭔가 그리디해지는 거예요. 그러니까 첫 번째 뭔가 생성을 내가 잘못했다. 그러니까 아까 얘기했던 것처럼 I 다음에 very를 생성했다. 그러면 이거는 볼 것도 없이 이거 완전 틀린 문장이 되는 거예요.
네.
네, 그래서 이제 기본적으로 이제 디코딩 그러니까 이거를 테스트 타임에서는 이 RNN을 가지고 하면 기본적으로는 그리디 할 수밖에 없어요.
네네.
그리디한 어프로치를 쓸 수밖에 없고
네.
그래서 이제 뭐 어떤 그리디한 어떤 그 방식이 한계점, 지금
네.
이런 한계점.
네네.
그러니까 얘를 골랐을 때 이 뒤쪽이 그럼 완전히 여기서 하여튼 첫 번째로 잘못 판단해서 잘못 골랐으면 뒤쪽도 그냥 다 망가진 거고 뒤쪽에서 회생 불가능인 상태가 될 수 있는 거잖아요.
네네.
그러니까 이 랜덤하게 고르는 거는
네.
그런 회생 가능성이 조금은 있다라고 볼 수 있는 거고.
네네. 하나만 더 여쭤보면 그러면 이제 티셔 폴싱을 쓰게 되면 약간 병렬적으로 이제 이 연관 관계가 그러니까 트레이닝 과정이 안 해도 되니까 병렬 가능하다 그러는데 근데 그 트레이닝 과정에서는 얘가 이제 학습이 돼야 되는 거잖아요. 결국 얘가 얘 위에 있는 H한테 뭔가 전달을 해줘야 되는데 그럼 그런 의미에서는 결국 얘랑 얘랑 연결이 돼 있어서 병렬적으로 따로 실행한다는 게 어떤 정확히 의미인지가 어차피 얘를 하려면 얘도 알아야 되는 게 아니에요.
그러니까 티처 폴싱은 병렬화가 돼도 안 돼요.
네.
티처 폴싱을 해도 병렬화는 순수한 의미에서 병렬화는 안 되거든요.
네.
근데 이제 그 병렬화가 어디까지는 되냐 하면 아까 두 개로 나눈 거가 어디 있었냐? 그 W 그러니까 HT가 요 두 가지로 나뉘는 거 있잖아요.
네.
요 두 가지로 나뉘는 거.
네.
지금 이 포뮬라에서 병렬화가 그러니까 한 방에 모든 타임 스텝에서 다 구해질 수 있는 거는 그래도 이 부분은 다 병렬화가 될 수가 있어요. 그렇죠?
네네.
그러니까 요만큼까지는 병렬화가 되는 거예요.
아, 네.
요거는 미리 내가 계산을 해놓을 수가 있는 거예요.
아, 네.
근데 이제 티처 폴싱을 안 쓰면 XT조차 어베일러블 하지가 않기 때문에 이 부분조차 이제 병렬화가 안 되는 거죠. 그러니까 이게 다 시퀀스가 되는 거죠. 그러니까 어쨌건 얘도 계산해야 되고 얘도 계산해야 되는 거니까. 그러니까 이 오른쪽 파트는 병렬화가 안 되는 건 맞아요.
네, 알겠습니다. 감사합니다.
네.